before we get started? Administrative, I mean like
No.
plan for the next couple of days. All right. I open up Google Earth instead of Google Calendar. Not what I meant to do. All right. So let's see. It's on screen. You guys should be able to see it in just a second. Can everybody see the screen?
Yes.
All righty. So we had done an introduction to the fundamental theorem of calculus yesterday, but I wanted to talk a little bit more about it today. And I'm going to start from the beginning and try and maybe go through it a little bit slower than we were doing yesterday. Okay. And then we'll get to the actual theorem. I'll write down the name of the theorem, or the formal statement of the theorem, and we'll actually do some problems with it. Okay. So we were trying to see what the connection was between areas under graphs and what we were calling antiderivatives. Okay, so let's first talk about what an antiderivative is. This is something from P1, right? We know how to find antiderivatives, but I want to give us some notation, some formal stuff, right? So antiderivatives. So we say f of x is the antiderivative of little f of x if f prime of x is equal to little f of x. Okay, this is a really silly way of saying it, but it's going to be really important for our notation. Okay, so as an example, we could have little f of x is equal to x squared. What's the antiderivative of x squared going to be?
X cubed over 3
Good. Well, you're missing one thing there.
plus C.
Plus c, right? Oh yeah, and for those of you who missed the plus c on the exam, that lost you a mark. Just letting you know. Not because of me, because of a mark scheme. All right, so this is how we do antiderivatives. This is common stuff. We've been doing this since P1, but I wanted to establish this notation just so we see exactly what's happening here, okay? So we've got f of x, little f of x is our function, big F of x is our antiderivative of that function. And the way that we notate that is we say big F of x is a function such that the derivative of big F of x is equal to little f of x, all right? And we were using some notation for this. We were saying that big F of x is like the integral, this little curvy thing, of little f of x. Right? Does that make sense? This is just a recap. This is nothing new.
Yes,
Makes sense.
sir.
Makes sense. Makes sense.
Okay. So this is going to be our notation going forward. All right. This thing right here. So what I'm going to do is I'm going to show you guys that you can actually come up with this same concept, this big f of x equaling like an antiderivative of little f of x, without actually making a reference to an integral at all and just looking at areas under a curve. Okay, so that's what we're going to do. So let's make a new page here. So we're going to say, let's look at a curve. I'll just draw some coordinate axes real quick. Decent coordinate axes. So we've got that, and we've got this. We're going to turn to Desmos in a second anyway. And let's draw a little curve. So we'll say our curve looks like this, same one that I was doing yesterday, kind of. All right, so this is our little f of x. And say we want to try and determine, again, remember we were trying to determine areas and how we could actually find areas computationally. So let's try and determine the area under this graph from some a to b that I'm going to draw. Okay, so we'll say this is a right here on the x-axis, and this is b over here on the x-axis. Okay, so we'll say this is the area that we're trying to determine, right? The area between these two things. All right, so we're trying to find this area, and the way that we're going to do it is we're going to approximate it really badly, okay? So our approximation is going to be a rectangle, this blue rectangle, going from A to B, right? But the height of the rectangle is going to be determined only by the point where where that rectangle meets the curve at A, okay? So this height right here, what is this height?
F of A.
F of A. Good. All right. And so we'd say that the area of the rectangle, this is exactly what we were doing yesterday, right? No difference. The area of the rectangle is going to be the height, which is F of A, times the width. What's the width?
F of B minus F of A.
No,
Oh, B minus A.
just B minus A, right? It's just the difference of the x coordinate. So our area of our rectangle is going to be B minus A. All right. And the area of our red thing, well, the area of our red thing, we don't know exactly what it is. Okay. We'll say that the area of the red thing is just called area of red thing. All right. It's the thing that we're actually trying to figure out. And so the concept that we were trying to develop yesterday was, well, if this is a really bad approximation for a rectangle, right? What could we do to find a better one? Well, there's two options. One option is to say, let's make more rectangles. So this is how we did it a while ago. So we said we can make more rectangles. We could do two rectangles instead. Have one rectangle have a height of A, right, or F of A. Have another height of F of the average of A and B right in the middle, right? So we do two rectangles, we get a slightly better approximation. It's still a bad one, but it's a better approximation. And then we could say, how can we make that better? Well, we could add 4 rectangles, right? Or we could do 20 rectangles, or we could do 1,000. And we're going to get a pretty good idea of what the area is approximately, okay? That's one option. And the other option is to say, well, let's say for a second that we don't want to actually find this area of this red shape. Let's find the area of a slightly different region. Okay, so I'll add another point here. We'll call it like point C. Okay, say we want to find the area of this purple region. Well, what we can do is we can say, well, let's do the same thing we did before with our rectangle approximation. Okay, we'll do a rectangle like this. It's going to be yellow now. Okay, the height of this rectangle is the same as the blue one. It's still F of A, right? So the height here is still F of A. The width is still calculated the same way, right? So the width here is still C minus A, but now you can visually see that the area of the yellow rectangle and the area of the purple region are much, much closer to each other than they were originally, right? So somehow by taking B and shifting it closer and closer to A, we get a much better approximation of our area, right? By using only one rectangle, right? We're only using one rectangle here. So somehow the area of the actual region underneath the curve, if we let B get really, really close to A, gets close to the area of this rectangle. Do you guys agree with that so far?
Yeah.
Yep.
Okay. So in other words, we're saying, in a slightly more formal sense, we're saying as B gets closer to A, the area of our rectangle gets closer to the area of our actual region under the curve, right? So area under curve. You guys see that? Do you guys agree? With only one rectangle, we're not
Yep.
doing multiple rectangles here, only one rectangle. So as we take the endpoints, we move them closer and closer to each other, the area of the rectangle is much closer to just the area under the actual curve. Okay? Do you guys agree?
Yes.
Okay. And if that's true, then that means that, and this is kind of silly, but this is a real thing. It also implies, I'll keep it in black, it also implies that the area of the rectangle divided by B minus A gets closer and closer to the area under the curve divided by B minus A, right? Do you guys agree? I'm just dividing both things by a constant.
Yep.
Okay. But here's the thing. We actually have a formula for area of the rectangle. It's just F of A times B minus A. So what happens if we divide that by B minus A?
Yeah, area divided by b minus a would just be the height. So
Exactly. It's just F of A, right? So this thing here has to get closer and closer to F of A. So what we've just said is that the area under the curve divided by the width of the rectangle, right? Divided by the width of the region, as we let B get really, really close to A, as we let the region get really, really small, this has to be really close to the actual function at that point, all right? So this is what we were talking about yesterday, and we had a Desmos thing to help us visualize it. So let's cross over to Desmos real quick. So this is just a region under a curve, okay? This is actually x squared, I'm pretty sure. And so if you look at it, oops. If you look at it, let's actually plot our f of a real quick. f of a. So our f of a, which is at this point, that orange point right there, is just the point 1, 1.
No, no,
Okay?
en mi conciencia está, Domingo, no te preocupes.
Hey,
Bueno,
Danny. Nice to
Chao,
be joining
Domingo.
Turn your
us.
mic off.
Okay. All right. So if you notice, right, our f of a is the point, is the point 1, 1, right? So when we plug in a is equal to 1, f is equal to 1 there as well, right? That's that coordinate. And the area here, the area under this red curve is given exactly by this formula right here. So the area under this region is 1.33000, so on and so forth. Okay. You guys see that? And as we actually, sorry, this is not the area. This is the area divided by b minus a. So this is the area right here. The area is 0.3999. Okay, so we'll call this. No, we'll just leave it like that. So that's the area, and our actual region that we were talking about. Let's see, big F of b. It's annoying to type on an iPad. Minus big F of a divided by that interval. So divided by b minus a. All right, so that's 1.330 whatever. Okay, so if you look back at our live board session, what we're saying is the area under f of x, f of x is going to be calculated eventually as big F of b minus big F of a. I'll show you how that's true in a second. And if we divide that by b minus a, that's the ratio that we're looking at. Okay, so what I've claimed is that the area divided by b minus a, it looks like it's lagging. I'm actually back in Desmos. Can you guys see that? Or is it still stuck on the live board session? There we go. Everybody see Desmos?
Yes.
Okay.
Yes.
All right, so as we let B get really, really close to A, so let's say it's not 1, but rather like 1.05, well, you can see that the area divided by the interval, which is this thing right here, right? It's the f of b minus f of a over b minus a, is pretty close to actually f of a there, right? It's 1.05 instead of being 1. And we can make b even smaller. So instead of making it 1.05, we can make it 1. No, actually, that's that's good. So if we make it 1.005, now we're at 1.005 for our area divided by our width of our rectangle. And you can see this rectangle that we'd be calculating is really, really thin, right? And so is the region. And so they're only off by that tiny little triangular piece right here, right? This is the difference between the rectangle approximation and the actual area. And that's a tiny, tiny, tiny little region if we zoom out all the way, right? It's that tiny little triangle. And so we can make this even smaller, do like 1.005, and we can see, yeah, we're getting much, much closer, right? It's now 1.000761, whatever, okay? So that's really, really close to the actual value of f of a there, okay? Is everybody okay with that? So let's actually, sorry?
If some of the times you have like a triangle, most of the times,
Mhm.
instead of doing a square, why don't you do a trapezium?
You could equivalently do a trapezium. It's just that for doing a rectangle, it's easier to just divide out by b minus a and get just the function back, right? It would be a much better approximation to use a trapezium. That's absolutely true. But to actually derive, right, hand-wavingly derive the fundamental theorem of calculus, rectangles are easier because the formula for the area is much easier, right?
Mm-hmm.
Does that make sense? But you're right that yeah, Eva, I think it is lagging for everybody. It's even lagging for me looking at my own screen. Um, but Fernando, to answer your question, doing a trapezium is a much, much better approximation. And we will eventually talk about something called the trapezium rule for actually approximating areas like this. You're absolutely right. Okay, so let's actually analyze what's happening here, because up until right now, I've just said this abstract thing with the area divided by the actual area under the curve divided by the width of these rectangles is giving us approximately the function as long as the rectangles are really, really thin, okay? And this is not that surprising. It's just basically saying if we take a tiny little region, we find the area of that thing, and we divide it by the width of that thing, it should be approximately the same as the function at that point. It should be approximately the same as the y-coordinate. So let's see, what does this have to do with antiderivatives? Because this is the interesting thing, right? How does any of this have to do with antiderivatives? Well, let's formalize it a little bit. So we're going to say we're going to say, given a curve, I'll draw a curve. I'm going to do a really interesting curve. I don't think you guys have ever seen me draw this curve before. It's going to look really, really weird. Never drawn anything like it in my life. Doesn't look at all like any of the functions that I've ever drawn before. It's going to look something like this,
Sir,
okay? Yes.
It just looks like you dropped a hair on your screen.
That's essentially what I did. That's what I model all of them, actually. After I just pull a hair and I throw it down on the screen and I just trace it. That's giving me a creepy visual now. I don't want to think about that. All right, so we're going to define a function called a of x, okay? And a of x, right? A of x, just like this. A of x is going to be the area underneath the curve. Let's say from, minus infinity. Well, we don't have to go to minus infinity, right? We'll say from 0 until x, right? So this is the area under f of x from 0 up to x. From 0 up to x. Okay? And let's say that we've got a point here called x is equal to a. And so what a of a would represent, right? A of a would represent this region right here. Okay? This is a, big A of little a. Are you guys okay with the name, how I've defined this function? It's just the area under the curve from the origin up to that point. Okay? And we'll say that a of b, if this is b right here, and remember, this is just a re-derivation of what we did yesterday. If this is b, then a of b would just be the area. Yes, go ahead.
Wouldn't it technically be a of a minus a of 0?
Yes, but here I'm actually defining it to be the area from 0 up until that point.
Okay.
Instead of from minus infinity. Yesterday we did it from minus infinity, and if you wanted to make this what we're going to do right now really rigorous, then you would have to do it from minus infinity. But I'm not too concerned with it. I'm just concerned with the intuition here instead of the actual derivation. But you're right. So this blue region then, this would be a of b, right? Just the area from the origin up to the point b. Okay? Do you guys agree? That's an excellent question, Luis. We'll get to that later. You're very, very, very right to ask that question. Okay, I mean, there's a problem with what you just asked, and it's a very good thing to bring up. We'll all address that very soon. For those of you who didn't see what he asked in the chat, he asked what happens if the function goes below the x-axis, and there's a very weird concept that arises when you do that. And so what we're going to be concerned with right now is we're going to try and find the area from a to b. Okay. So that's this area right here, this purple area. So in terms of this big function a, what would this purple area represent?
A of b minus a of a.
Yeah, that's exactly right. This is going to be a of b minus a of a. All right. Just the area underneath the curve from the origin up to b minus the area underneath the curve from the origin up to a. It's the difference between those two areas. All right. I think maybe red, blue, and purple were not the best choice of colors because they all kind of blend together, but that's okay. All right. So we've got this purple area that's between the two of them. And what we just said is that on the previous slide, if you look at it, what we just said is that this area, which is the purple area in question, as we let b get really, really close to a, this should just be the same thing as the function, right? If we divide by b minus a, it should just be the same thing as the function, okay? So what that means is, as b gets close to a, right? So we'll say from previous slide, we just showed that as b gets closer to a, then a of b minus a of a gets really, really, or divided by b minus a, gets really, really close to just f at the point a. Do you guys agree? I should actually put like an arrow. Gets closer to. Doesn't equal. Gets closer to. This is exactly what we did before, just with some notation now. All right? You guys okay with that?
Yes.
Yes.
Okay. Let's take it 1 degree further in rigor. Okay, 1 tiny degree further, because I'm going to show you guys that what we have just written down, this is kind of hidden, but this is the definition of a derivative. All right.
Do you mean of an integral?
No, I mean of a
Of a
derivative.
derivative?
I will
Oh.
show you what I mean by that.
Okay.
So let's take it one tiny, I'm sorry to do this, one tiny degree further in complexity. It's not, I promise you, it's not overwhelmingly difficult at all. I promise. All right, so let's do another screen. We're going to do another very unique and interesting graph that you've never seen before. Again, okay. I should win a Nobel Prize in art for coming up with such original functions every single time I draw one. All right, so now we're going to say, let's just take a look at a of x, okay? Let's write down some point x. So we'll say this is, some variable point x. And instead of calling it a and b for our 2 points on the x-axis, let's call it x and x plus h. Okay? We'll say there's 2 points now. This is x, and this is x plus h. And so the width between them, the difference between the two of them is just h. You guys agree? H could be anything here, right? It's just a constant. And so the region between those two, the area of the region between those two, which I'll shade in red, this area, using the notation we have with A, right? This region is given by, so the area in red is given by A of x plus h minus A of x. Does everybody agree?
Yep.
Yes.
Yeah.
Yes.
And we also know that as x plus h gets closer to x, so as x plus h gets closer to x, then the area of x plus h minus A of x divided by x plus h minus x needs to get closer and closer to just f of x. Do you guys agree? It's the exact same thing I wrote down on the previous page, just with x's and x plus h's instead of a's and b's. Everybody okay with this?
Yep.
Yes.
Yeah, are you sure? All right, so let's do a little bit of simplification. This is just the same thing as a of x plus h minus a of x divided by, well, the x's on the bottom cancel, so we're left with just an h. And guess what? If we let h go to 0, which is the same thing as letting x plus h go to x, right? This just means h goes to 0. We have just written down the definition of a limit, right? This is the limit as h goes to 0 of a of x plus h minus a of x divided by h equals f of x. So what it's telling us is that this function that's giving us the area, the derivative of that function is the original function of the curve. All right. And so what is that? What is the only option for big A? What does it have to equal? It's got to equal our antiderivative of f of x. Does that make sense?
Yes.
Does everybody see that? It's a nuance. It's not the clearest thing in the world. Guys?
Yes.
Okay. It tells us a lot here, right? It tells us that whatever this function is, a of x, right? Or we previously called it big f of x, whatever this function is, the derivative of it has to be the curve itself. But even more importantly, if we wanted to find the region underneath the curve of little f of x between any 2 points, all we have to do is evaluate this big A function at the endpoint and subtract off the area up until the left end point, right? It just basically tells us that to find an area under a curve, we find an antiderivative, plug in our rightmost endpoint, and subtract off, plugging in our leftmost endpoint. So in other words, I'll summarize everything up now with the fundamental theorem of calculus. This is the actual statement of the fundamental theorem. The fundamental theorem of calculus tells us that if big F prime of x is equal to little f of x. So in other words, this means if big F of x is the antiderivative of little f of x, okay, that's what that f prime of x equaling little f of x is equal means. Then the area underneath little f of x from a to b, from x is equal to a, from x is equal to a, up to x is equal to b, right, is given by big F of b minus big F of a. All right. So in other words, to find the area under a curve over a certain region, right? So I'll draw you a little picture because I don't think that you've seen my function enough. And I think that you guys think that joke is hilarious. That's why you keep muting your mic so that we can't all hear you laughing.
Haha.
Thought so. One brave soul brave enough to unmute their mic. All right, so if we have the region from A to B, right, this area, that's this area that we're calculating. All we've got to do is find the antiderivative of f of x, plug in b, and then plug in a and take their difference, okay? And the notation for this, right, so the notation is that the area is given by the integral from a to b of little f of x dx, and it's equal to f of b minus big F of a, okay? This thing that I just written in blue is the mathematical statement of the fundamental theorem of calculus, okay? The fundamental theorem for a reason. Think of all the things that it's tying together. It's tying integrals together with areas and derivatives, okay? So we have just taken, there's a whole side of calculus called differential calculus. There's a whole side of calculus called integral calculus, and this is where those two sides of calculus meet, right? They meet at this one fundamental theorem, which is why it's called the fundamental theorem, all right? And we haven't actually proven anything here. We've just sort of built it by looking at curves and looking at rectangles and comparing the two of them together, right? So just be aware that if you were to actually rigorously prove this, there'd be a lot more work that goes into it, okay? But this is just by looking at Desmos and playing around a little bit, we've been able to come up with this formula, right, or this theorem. Okay, so this is the backstory, right? This is where it comes from, but how do you actually do it? Well, let's do a couple of examples, all right? And then we'll get to Luis's question, which is a really, really, really important question that he asked, okay? Really, really important question. I'll show you that it's an important question with an example in a second. All right, so let's take a look. What if we have, we want to find the area. So our problem is going to be find the area under the graph or under the curve given by f of x is equal to x squared, okay? Actually, let's do x for right now, because I'm going to show you guys that this actually works in two different ways, okay? So we're going to try find the area under the curve of x from the origin to, let's say, 2, 2, okay? So before we actually do anything, let's try and decide how we would have done this before, right? If we hadn't had integrals in our toolbox or the fundamental theorem of calculus, how would we have done this before? Well, we should always start by drawing a diagram, right? So f of x looks something like this, or f of x equals x. There's a straight line that looks something like that, okay? And it goes down to the left, but since I only want to do it from 0 to 2, I'm not too concerned with including that information, okay? So here's the origin, that's 0, 0. Then we've got 1, 1. I'll make my scale like every 3 is 1, so this is 1, and this is 2. And so what we're trying to find here is the region underneath the graph of f of x is equal to x from 0 to 2. So it's this red triangle thing that I've drawn right here, okay? So how would I have done this classically, right? So, classically is kind of a bad word, but like before we did integrals.
Half base times height.
Good. We know that the area of a triangle is 1/2 base times height, okay? So what is the base here?
2.
The base is 2. Good. And what is the height?
2.
It's also 2. So we have a base of 2 and a height of 2. And so the area is just 1/2 base times height, which is 1/2 times 2 times 2, which is 2. It's not very interesting, right? Not very interesting at all. And so what would we do if we were trying to do this in the language of the fundamental theorem of calculus? Well, we would say this area, I'll keep it in blue. So the area should be equal to, by the fundamental theorem, the integral from 0 to 2, right? Remember that we're integrating across the x-axis. This is our a is 0 here, and our b is 2 here, just like in the fundamental theorem, of x dx, all right? This is what we'd write down before we actually solved anything. And then we have to say, okay, well, what is the antiderivative of x? What function has a derivative equal to x?
X squared. No.
X squared over
Half
2.
half
X squared over 2. Good, right? Although you're missing the plus c, we're going to include it for right now. Those of you who already know what I'm about to do, and you know that there's a shortcut, just stay quiet for 1 second because you're right, but I want to do it the long way first, okay? So we'd write down our antiderivative is x squared over 2 plus c, okay? And now there's some notation here that's convenient because this is not what our integral is equal to. This is what our antiderivative is equal to. So to make this expression actually true, we usually do a vertical line, okay? And we put the same limits of integration here in our vertical line. So we'll say we still haven't plugged in our limits, 0 and 2. This is just a notational thing, okay? All right, so our area should be given by this formula. And so if we look back at our previous slides, I'll reference them real quick. Right here, our previous slide, says that all we have to do to find out our area, I know it's probably lagging for you guys, is plug in b into our antiderivative and plug in a into our antiderivative and take their difference. So let's do that. So in this case, b is 2, so we've got to plug 2 into our antiderivative. So that's going to be 2 squared over 2 plus c. Keep in mind, we have no idea what c is. And then we're going to plug in 0 into our antiderivative. So that'd be 0 squared over 2 plus c, okay? Again, we have no idea what c is. Well, we can actually simplify this a little bit. 2 squared is just 4, right? So we've got 4 over 2 plus c for our first term. 0 squared over 2 is just 0. So we've got minus 0 minus c. And so something interesting happens, which is that the c's don't matter at all, right? They cancel each other off. The c's go away completely, all right? The 0 also obviously goes away, and the 4 divided by 2 becomes a 2. And so guess what? We get the exact same answer that we got by doing the triangle. Okay, now this particular problem, and this very particular problem, this is really silly, right? Why is this a silly thing to do? Well, because the integral's much more work than just using trigonometry, right? Do you guys agree?
Yes.
Yep.
So why would we use this? Well, because not every shape is something that we know the area for, right? So let's do a different example. Before I go on to doing a different example, are we okay with this? Does this make sense?
Yes.
Yes.
Are you sure?
Yep.
Okay. So let's do another example. There's a bee bothering me. Hopefully it doesn't sting me on camera. That'd be embarrassing. All right. So let's do another one whose shape is not as nice. Right? Let's do the integral under the graph of, let's do 1 over x. Okay, so 1 over x looks something like this. Right? So this is 1 over x. Okay, and there's another part right here, which I'm not going to care too much about for this particular problem. So let's say we want to find the area under the graph of f of x equals 1 over x. And we'll say from 1 up to 2. Okay. So there's a reason I'm not starting from the origin. Does anybody have any idea why I'm not starting from the origin for my limits?
It's infinite.
Right. It's going to explode, right? You can see this thing it's got an asymptote at the origin, right? It's going off to infinity. And so finding the area under that is a very tricky thing, right? It's called divergent. There are some cases where you can have infinite things like that actually give you finite regions, but in this case it won't work. Okay? So that's not going to work. So we're going to do it from 1 to 2. Oops. So graphically, what this means is I'm trying to find this area right here. If this is 1 and this is 2, I'm trying to find this region right here. Now, I can't do any basic geometry, right? There's no fundamental shape that this is equal to that will give me my exact area, right? This won't work. It's not a trapezium, although it kind of looks like it in my picture, right? Because it's got a curved top. It's not a, it's not a triangle and a rectangle, because that would just be a trapezium. There's no fundamental shape here, right? So we can only do this by means of integration, okay? By means of taking an antiderivative. But that's okay, because the fundamental theorem of calculus tells us that the area here should just be the integral from 1 to 2 of f of x dx. So in this case, f of x is 1 over x. So this is the integral from 1 to 2 of 1 over x dx. Now, you guys tell me, in this whole curriculum this year, we only know how to find antiderivatives and derivatives of what?
Polynomials.
Of powers of x, right? So, oh, you know what? Let me change it ever so slightly. It's not going to actually change my picture or anything at all. Okay, I'm just going to put an x cubed here. I just remembered that I did one.
Is it just because you told us that n cannot be minus
It's the
1?
exception. That's the exception. I didn't realize that. So this, it's the same problem basically, right? My picture even looks almost identical. It's just that now I've got a 1 over x cubed instead of a 1 over x. All right. And there's a reason for that we'll get into next year. We won't get into it right now. So again, my question still stands, right? We only know how to find the integrals and derivatives of powers of x. So how can we express this as a power of x?
X minus 3, x to the power of minus 3.
Good. So it's the integral from 1 to 2 of x to the power of minus 3 dx. And so what is the antiderivative of x to the power of minus 3?
It's minus 3x to the power of minus 4 divided by 4. Minus 4.
Not quite. That's
No,
that's
it's x to the power of minus 2 divided by minus 2.
good. Remember that when we're doing antiderivatives, that if I have little f of x is equal to x to the power of n, then big f of x is equal to x to the power of n plus 1 over n plus 1 plus c. Okay. So in this case, adding 1 to minus 3 gives me a minus 2. And so we're going to divide by minus 2 as well. And then this is probably the last time that I'll do this. We've got a plus c here. And then we've got our notation, which is the vertical bar from 1 to 2. So this tells us we've found our antiderivative now. Now the only thing that we have left to do is plug in 2, plug in 1, and take their difference. Okay? So what happens if we plug in 2? Well, let's just do it. We get 2 to the power of minus 2 over minus 2. I'll simplify this in a second. Plus c minus, right? Remember, there's always a minus sign. 1 to the power of minus 2 over minus 2 plus c. What is 2 to the power of minus 2 over minus 2? What does that equal?
1 over 8.
1 over minus 1 over 8, right?
Yes, my bad.
So we get minus 1 over 8 plus c. And then we get, what is 1 to the power of minus 2 over minus 2?
Minus a half.
Good. Minus 1/2 plus c. Now, if we open up those brackets and try and simplify, we're going to get minus 1/8 plus c minus minus, which becomes a positive 1/2 minus c. And again, we can see that those c's, we can see the c's, those constants, those cancel each other out, right? And in fact, that's always, always, always going to happen. If you are doing what is called a definite integral, right? Definite integrals are when you're trying to find areas. So whenever you've got an integral that's got these limits on them, like from 1 to 2, so on and so forth, you do not need to include c. All right, let me write that down so it's very clear. For definite integrals, only for definite integrals, so only for definite integrals, which means areas, okay, you do not need to include plus c. All right. If you are doing what is called an indefinite integral, which means you're just trying to find an antiderivative, or in other words, you are just trying to find big f of x, if you do not include plus c, it is wrong. All right. I know that I've said that to you guys now a bunch of times this year, but it is extraordinarily important that you remember that. It'll be even more important next year, but as a fundamental concept, it's very important. Okay. So when you're doing definite integrals, meaning when you're trying to actually find an area, you don't need to include the plus c. only because that plus c is always going to go away. All right. All right. So what would this actually equal? Well, it's just equal to a half minus an eighth. So what is that?
3/8.
3/8. So the area, this little red shape that I've drawn here, is 3/8. Okay. And this is something that we would not have been able to do by using regular geometry. It wouldn't have worked. There's no technique for it, right? This is not a standard shape. So we have to turn to integration in this case. All right. Is everybody okay so far? There's one last thing that I want to do.
Yes. Are you going to talk about underneath the
Yes.
x-axis? Okay.
That's the very last thing that I want to do. Is everybody okay with this so far?
Yep.
Okay. So let's just do another example. And I'm going to show you a really weird conceptual thing that happens here. Okay. This is just assuming that we're doing the exact same thing again, but this is a new example. Okay. Let's try and find the integral or the area underneath the curve of x cubed. All right. So let me draw my little axes and I'll draw x cubed as well. So x cubed looks something like this. And don't shout out any answers. I know that there's some of you who are going to know what's going on here, but I want everybody to come to the same conclusion on their own. Okay. So this is our graph of y is equal to x cubed. And my question is going to be, find the area underneath y is equal to x cubed from -1 to 1. So let's draw a picture here. What does this mean? Well, if this is -1 here, okay, so this would be -1. I know my scale's not great, but that's okay. And this is 1, what would it be? 1 here. All right, so we're trying to find this area right here. This is the area we're trying to find. Okay. Again, please don't shout out answers. Those of you who I know the answer. So the fundamental theorem of calculus tells us this should be the integral from -1 to 1 of x cubed dx. All right. So what is the antiderivative of x cubed? What function gives you a derivative equal to x cubed?
X to the power 4 over 4.
Excellent, right? X to the fourth over 4. And then we technically would need our plus c here, but now I'm going to start dropping it because we don't need the plus c when we're doing areas, right? So we'd have an x to the 4th over 4 from -1 to 1. And the fundamental theorem of calculus tells us just plug in the top limit, plug in the bottom limit, and take their difference. So this would mean plug in 1 to the power of 4 over 4 and subtract off -1 to the power of 4 over 4. Well, this is just 1/4 minus 1/4. What is 1/4 minus a fourth?
0.
0. Okay. So this is strange because the fundamental theorem of calculus is failing us here, right? It's telling us that there's 0 area, but I just drew the area and it's clearly not 0. Well, guess what? Anything that's below the x-axis, okay, so this is a problem with the fundamental theorem. So the problem with the fundamental theorem, I'll call it the FTC, fundamental theorem of calculus, is that area below the x-axis is considered to be negative. Okay, and this sort of violates something that you guys have known since you were, I don't know, children, right? You can't have a negative area. That doesn't make any sense. Well, the integral does not distinguish that impossibility, right? So anything that's below the x-axis is considered to be negative. And this is actually really important. If this weren't the case, we wouldn't be able to use integrals for a lot of physics problems, okay? You can think of what this situation is right now, that what we've just done, you could think of this as being an equivalent to like displacement, right? Imagine I travel 4 feet forwards, or 4 meters forwards, and then I travel 4 meters backwards. How far have I traveled overall from my starting point? 0, right? I've gone 4 feet forwards, or 4 meters forwards, and 4 meters backwards. I'm back where I began. That's very similar to what's happening here, right? It's saying you go a certain amount below, you go a certain amount above, they come together in the middle at 0, right? That's essentially the exact same thing. If integrals did distinguish, but if they made the distinction that area below the x-axis was still positive, we wouldn't have applications of integrals in things like mechanics problems where I try and find the total displacement, right? I would have to be very, very careful about how I did it, because 4 meters forward and 4 meters backward would be considered 8 meters. But we know that would be wrong, right? I'm not 8 meters away from my starting point. I've traveled 8 meters total, but I'm not 8 meters away from where I started. Okay, so it's a very analogous thing here. We'll go into that a little bit more in detail next year when we talk about how we can apply integrals to other situations other than just finding areas. But keep in mind that that's a very similar thing that's happening here. Okay.
Sir,
Yes, go ahead.
for that problem, could you? I don't know if you can take the integral of stuff in between absolute bars.
Absolutely can. You absolutely can. You've got to be very careful when you do it, but you can. You absolutely can. It's a very, very good observation. And not only that, but you can actually take absolute values of integrals themselves as well. So if I wanted to actually find the physical area here, okay, so here's a thought. The fundamental theorem of calculus is not allowing me to solve this problem in the way that we are used to seeing it, right? Because it's giving me an area of 0 when it's clearly not 0. But what if I wanted to actually find the area of this shape if I were to draw it on a piece of paper like I have done right now? Like, how many squares does it actually take up on the screen? Well, what I could do is I could take the integral. I could find this area. We'll call this area 1 by taking the integral from -1 to 0 of x cubed dx. Okay, I'll call this area 2. This is the integral from 0 to 1 of x cubed dx. All right, so I can find each of these areas individually, and then I would say if a1 is negative, so I'll say if a1 is less than 0, sorry, I know I'm keeping you guys a little bit later, right? If a1 is less than 0, just make it positive, right? Make it positive. And same thing with a2, right? If a2 is less than 0, which it's not in this case, make it positive, right? And the total area is going to be a1 as a positive number, which is what these bars mean right here, right? This means it's always positive, plus a2 with bars around it. Okay, so you can still solve this problem. You just have to break up your integral over 2 intervals, right? You can't just do the integral from -1 to 1 because it's considering all the negative area to be negative, right? So what you do instead is you do it over the negative region first. You make that a positive number, and then do it over the positive region. Make that a positive number. It's not a positive number, and add them together. All right.
Sure.
Yes.
But say you have like a parabola with a negative x squared coefficient
Mhm.
that is in, say, the 4th quadrant, right? And
Okay.
you want to find its area. Do you do the same, like you ignore the negative values?
Well, okay, so it depends on what you mean. Do you mean the area like below the curve, or do you mean the area up to the x-axis?
Below.
So keep in mind that the area below the curve is going to be infinity, no matter what
But
region
what
you're
if
over.
like you get yeah, but if you want to find like an exact part of it?
A finite part. That's the
Yeah.
very next topic. And
Okay.
you're right. We will have to start talking about how we find areas between 2 curves, right? So these same concepts here will still apply if we wanted to say find. I'll just leave you guys on a thought. If we wanted to find the area, let's say we've got 2 curves now, right? So we've got my coordinate axes, and say I've got, this is my first curve f of x, right? My original beautiful curve, and then I've got another curve, let's say g of x, that looks something like this. What if I wanted to find the area between these two? Right? I should be able to find the area between these two. And we will be able to find the area between these two as well. Okay? That's where I'll leave it today, guys. We'll come back to this stuff when we meet again. All right? Hopefully this is making sense for some of you. We've got to get a move on. We've got a decent amount of material left to do. We've got to talk about areas between curves like this, and then we've got to talk about area approximations, and we don't know how to find the integral, right? So there are certain integrals that we can't do yet because we haven't learned the skills, and even further, there are integrals that I can't do because they're impossible to do, right? And we still want to be able to find areas under those curves, even if they're impossible to do. So we have an
Is
approximation
it
technique.
like the further maths one, the e to the power of minus x squared over
As an
2?
example, yeah.
Mm.
Yeah. But I'll
Yeah.
show you guys in regular maths a way to find an approximate value for that integral. Okay?
Okay, sir.
All right, guys, that's it for today.
Bye.
Let me know if you have any questions or
Yes,
anything like
sir.
that, okay? I'll try and make your M1 video as soon as possible, okay? I don't know if you're still here. I think she left. Okay. Somebody pass that information here.
Bye, sir.